Everyone is manning their post. They all know that failure is not an option. As the flight test crew push the A380 towards Mach 0.96, the slightest abnormal vibration could cause serious damage or even complete destruction of the aircraft. Mach 0.94, Mach 0.95. The A380 begins to tremble relentlessly, but with the aircraft holding together, the crew members try to shake off their nerves. Reassured that they can attempt the final push, the crew takes one more dive. Within seconds, the aircraft hits the ultimate speed of Mach 0.96. In the telemetry room, the engineers celebrate the fact that their aircraft is now flutter test certified. And with the plane back on the ground, the test flight crew can finally breathe a sigh of relief.
Je suis bien content. Je suis bien content.
Fernando, are you happy?
Oh, very happy, very happy. We took good care of him. He took good care of us also.
Stop. Let's try something else. I guess no narration with these. So as we warm up today, I guess we've still got a few minutes to go. So these are just some videos of typical things that go on related to understanding the behavior of structures in airflows. You all have had in your high school physics classes the Tacoma Narrows Bridge example of a bridge tearing itself apart near Seattle, near Tacoma, Washington, in the 1950s, due to this phenomenon called flutter and aeroelasticity. So aeroelasticity is the interaction of a fluid with an elastic structure. It's the essence of flight structures, wings, airfoils on planes, and how they behave. The previous video of the A380 going through its Mach 0.96, 0.96 of the speed of sound flight tests to make sure that under those quite high stresses that are applied that the aircraft doesn't fall apart. Understanding the behavior of something like the Tacoma Narrows Bridge is a constant wind flows across it, not particularly fast wind that's tearing it apart, but a constant velocity wind. Not so different from slightly different process, I guess, blowing over the top of a beer glass or top of a bottle, beer bottle or a soda bottle, and getting a resonant frequency out of it are all kind of similar behaviors. I'm trying to think what else we've got here. As we go, let's see what this is. Not a recent film, yeah, Flutter, I guess. So again, oh, includes Tacoma Narrows, yeah, good. So as a follow-on from the wind tunnel test you just saw, this is the behavior in reality, and that is this resonance being set up in a structure because it's typically due to the fact that if you have wind flowing across the deck, that vortices are shed alternately from the top of the deck and the bottom of the deck, and they fly downstream. We saw them a little bit in that small flow around a circular cylinder. We'll go back to that and look at them, but you have vortices at different locations in the wake, and that's because they're shed one after each other from the top and bottom. And you can imagine that when they're shed, there's a slight shock that's applied to the bridge. And if that shock is at exactly the same frequency as the resonant frequency of the bridge, like a guitar string being plucked, then it has these modes of deformation that if they get too bad, then they start tearing the structure apart, as they do in the case of the bridge. And probably you don't want to fly on that plane because it has a mode, a natural mode, which is directly the same. So its resonant frequency is exactly the same as the frequency of the airflow disturbance around it is causing it. So it's a reinforcing feedback that makes the behavior worse and worse, and makes for an uncomfortable flight, I would wager. And so those are the issues. Yeah. And so wind tunnels, of course, are one way that you can test that, because these apply the real behavior of the fluid around them. So you can do tests on airplanes in wind tunnels with wind, air, as the liquid, as the fluid rather, or you can do them in water. You could substitute them. You just have to know how to be able to translate the behaviors that you see in these different media between them. And of course, Buckingham PI is one way, the first step in being able to do that, in being able to figure out exactly what the controlling variables are that you should get right in your test so that the test is representative. And then the next step is to do a study on similitude, which we'll talk about today, that allows you to make sure that your experiments are comparing apples to apples. So I want to do that. I was one extra one. We saw the Airbus. I guess I don't have this playing in the background, and I don't know if this is much different. Let's look at it. We have some time this morning. I'll shut up for a moment. That's 4 minutes. We have 4 minutes. Of course, this was the golden age of things like aeroelasticity. This is the late 1950s, early 1960s. Sputnik, you know, the first satellite in space put up by the Russians, the Soviets, I guess, and Kennedy's call to put a man on the moon in the next decade, over that decade. And so understanding the behavior of flight structures, planes, missiles, rockets, was part of a national priority. And of course, fluid mechanics and understanding these behaviors in wind tunnels is a big part of developing that understanding. And so that's kind of maybe the heritage of some of this stuff. So yeah, maybe you call it a day there and look at what we've done so far. The last, I was saying before, when I arrived this morning, the last 2 times we've recorded, it hasn't come through, so it's just given the pen moving against a background of nothing, which has been unfortunate. So it doesn't matter. If you were here for the last 2 ones, for 9.1 and 9.2, then you'd have seen it in person, and if not, there are previous recordings that other people can refer to. So you'll recall that last time we talked about this issue of Buckingham PI. To be able to try and get the appropriate non-dimensional groups which defined our problem. Just to recap, you recall that the example we used was one of flow within a pipe, with the idea that we could define Buckingham PI theory is a formalism where you can define the behavior of a system in terms of its important parameters. And those important parameters, you kind of have to use some judgment, I guess, to be able to say what the key variables might be. But you could imagine that the dimensions of the problem would be important, some features of the driving forces that you apply and the response that you get out of it in terms of the velocities, and some parameters that represent the physical characteristics of the fluid. And if you remember last time, what we did in solving for the relationships that describe the flow of fluids within this system, and we made the case, I guess, that also the behavior that you get for flow in a pipe is actually not very different from the behavior you get for flow around a pipe which is closed off as its front and its back. But I guess the interest would be different. In flow in a pipe, we're interested in what the velocity is as a function of the friction losses that occur within the pipe due to these viscous losses, which will result from this. Flow around a plug, an external structure, we're probably more interested in figuring out the magnitude of the force that we have to hold this with to be able to counteract the flow that's coming past it. So there are different things we're interested in, but really it's actually the same process. And you recall that what we said was that we think that maybe the change in pressure is equal to some function of the other parameters. And the other parameters are the diameter, the velocity, and the fluid properties. And we chose to lump this length variable in the form of this, what we call delta PL. And so from our formalism for Buckingham PI, the number of parameters describing the system are 1, 2, 3, 4, 5. The number of MLTs was equal to 3, because all of those are represented. And as a result of that, what we called K minus N described the problem in terms of 2 pi variables. And those variables were, once we rearranged it in a certain way, they were pressure over length V squared rho times D. And it's some function of velocity, density, a characteristic dimension, and viscosity. That was the result we came up with. We could, if we wanted to, change this slightly so that this would be d over L times P over rho V squared. And the only reason for wanting to strip it out that way is that we have this is our, what we called our Euler number, which is the ratio of pressure forces to inertial forces, or destruction of momentum, V squared over 2G. And the other term, whoops, not that one. And the other term was Reynolds number. And we made the point that these are important parameters which we'll use when we talk about this idea of using similitude, which we'll get to a little later. What we could also have done is, instead of defining the behavior in terms of these 5 parameters, we could have defined behavior in terms of 6 parameters just by doing it like this. And in other words, having, in addition to those 4 parameters, 5 on the right hand side, d, velocity, diameter, viscosity of the fluid, and density, we could also have added the length variable. And if we'd have gone through this with the same analysis as this, then K would have been 6, N would have been 3, because mass, length, and time are all represented. And as a result of this, k minus n would be equal to 3 pi variables. And that would have been that the Euler number, p over rho v squared, is equal to some function of L over D or D over L, and Reynolds number would have come out of it. And so the parameters that come out of it aren't unique. They definitely are dimensionless by definition. We can check that, and we have checked that. And so if we chose, for instance, some extra variables, then what we'd find out if we added some extra variables such as relative roughness. Maybe we said the other day that we could think about on the side of this pipe, pipes aren't infinitely smooth with zero undulations. You could imagine that the magnitude of some roughness, which we'll call in this class epsilon, which is the height of this amplitude of this roughness in the walls, if we had that as an extra variable, then we'd have 7 of these, still 3, we can only have a maximum of 3, and so we'd have another variable which would be dimensionless, and it would be something like this. And so as you add extra variables to define your system, you end up with more dimensionless groups. And of course, some of these parameters might not be of any interest in controlling the system. But you have them anyway, and you could do experiments to be able to see and eliminate them, that they have any influence on the system. So the supposition from this would be, we did it before, but let's see, we had the fact that if we know what the actual relationship is for flow, I keep on doing that, flow in a pipe, I think we find out that the velocity, average velocity, is equal to the diameter squared over 32, 1 over viscosity dp dx. That's a solution that we get for laminar flow, which basically anchors the velocity of flow at the wall to be 0 and has a maximum in the middle. We're interested kind of in an average, an assumed average velocity, which we call v bar. And I think we did this last, maybe on Monday. We could convert this into something that we find useful in terms of what we think is controlling the system in terms of Euler number and Reynolds number by making this, I think, an Euler number. So to make it an Euler number, or 1 over an Euler number, we could multiply both sides by v. We could multiply both sides by density. And we could divide both sides through by P or dP. And our reason for doing that is now we get rid of this. We don't care about the dP. And if we write that out in longhand, we have rho v squared over p, which should be familiar. We have, take one of these d's here and put it over here. We're going to have what? We're going to have v times density times a characteristic dimension, d. And we're going to have mu rather. And we have an extra component here. And this, we can substitute this for L. So we have rho v squared over p is equal to d over L. Looks familiar, right? 1 over 32 is a property. And v rho d, which is the same as 1 over the Euler number is equal to d over L 1 over 32 times Reynolds number. And so we've gone from something, this is a solution for laminar flow, and so this is an equality, not an equality, this is an equation. This is a functional equality. And so if we drew this out, this relationship here would look like something like 1 over Euler number, Reynolds number in the laminar regime would be equal to, it's a straight line, right? For d over L equals 1, it would be equal to this. I guess for d over L equals a half, it would look like this. And so we'd have a whole series of these graphs because we have 3 variables, 3 non-dimensional variables, which came out of this as well. This suggested that there were 3, this one, and this one, before we added this 4th variable. This is what describes what goes on in the system. And so what we'll find is that as we look at these behaviors, what we could do, we could also plot this in terms of being the reciprocal of Euler number. We could plot it as being Reynolds number versus actually the Euler number. And if we do that, then we can imagine that low Reynolds numbers will have a big Euler number, and at high Reynolds numbers we'll have a small Euler number because of this relation. And this is the relationship that we've kind of drawn a couple of times before. This may be something like this. This is laminar, for which this is the equation. It's only laminar behavior. And we don't know what it's like at turbulent response, but what we'd find out is that if we looked at this at the turbulent regime, we'd find out that the behavior looks like this. We'll do that soon enough. And so the important thing is this is kind of an Euler number. So for pipe flow, we'll call this a friction factor. For external flows, we'll call this a coefficient of drag or a coefficient of lift. And for open channel flows, we'll call it a Manning number. But they're essentially the same behaviors. They are defining some frictional losses within a system which are due to the viscosity of the fluid, or 2 terms, I guess. This part here is due to viscous drag. This part here is due to inertial drag, accelerations that occur by making eddies. And if we look at the flows that occur in these, you might remember that we looked, we had this little pipe flowing last time if you're here. And within that pipe, we had some flow. And with this little tracer within the middle, absolutely for laminar flows, it was a straight line. But for Reynolds number flows, it started getting an undulation, and even faster ones, it got a larger undulation. And so these are because little vortices are occurring within the pipe that make it not laminar flow. Laminar by definition being a whole bunch of laminae that are sliding over each other. And so this behavior is true when we're looking at internal flows inside pipes, external flows around windmills, wind turbines or wind turbine blades, or open channel flows in a ditch, that there's some frictional loss that occurs by dragging the fluid against the structure, and that at very low Reynolds numbers it's just due to the viscosity, and at much higher Reynolds numbers it's due to the fact that we get this turbulence being developed. And so that's uniform in the things that we'll do. Okay? So the idea of similitude is that we can use Buckingham PI, very powerful method, to be able to figure out what the important dimensional variables are, and it will often turn out that they will be a ratio of lengths, L over D we had, a ratio of inertial forces to viscous forces in the Reynolds number, and a ratio of pressure forces applied on a structure relative to inertial forces around it, which are part of the Euler number. And that, if you like, is the essence of what we can use to look at similitude in terms of these three requirements that we alluded to last time that we have to satisfy. And that is, if we want to do wind tunnel tests on a small structure of a plane, we have to satisfy these three requirements to be able to use it in a quantitative measure to be able to figure out exactly what the lift and drag might be. This is just reiterating what we said. If you have two pi terms, then if you plot pi 1 against pi 2, there'll be some relationship and only one relationship. If you have 3 pi terms, as we did here, then you have 3 variables. You have pi 1 and pi 2, and then the other 3. So this is Euler number, this is Reynolds number, maybe, and this is length over diameter ratios that define the behavior. Okay? So, if we want to use models, and we can do an example with this, we basically have to have these three requirements. It's quite straightforward. The first is that the model has to be a correct representation of what we're dealing with. So the plane has to be scaled down in every dimension. So the model and the prototype have to look exactly the same as each other. So all basically this is saying is that the length of the model and the prototype have to be equal to the width of the model and the prototype. All of the dimensions have to scale. So it has to be a 1 to 100 scale model. And so you know what that means. So if this is the model, this is an appropriate model for this prototype, but this would not be, right? Because it's the length to height ratios are different. So that satisfies that you're looking at the proper structure. The second one is that you have to satisfy kinematic similitude. And that is an exposition of the fact that the flow regime has to be the same. And so let me just zip down through this to maybe what we'll talk about when we talk about external flows, because I think we've got some pictures of those. Maybe it's a bit further than I want it to be. It's a very specific diagram that I haven't. Oh, these are, yeah, actually it's a long way down. So let me try and find it. Yeah, this. So there's probably a better figure than that somewhere down here. Yeah, okay, this is good. So we could look at those 4, but we could also look at this. So this idea is that at low Reynolds numbers, so flowing around an object, so this is a Reynolds number of 0.1. And this is a Reynolds number of 50. So 500 times larger. The geometries, if you look at the streamlines that develop around here, this is firmly in the regime where viscous flows dominate, right? We made this point before that if you look at if you look at Euler number, which is also coefficient of drag, that we have this behavior. And this is Reynolds number, maybe this is 2000, and this is laminar, and it's controlled by viscosity, and this is turbulent, and it's controlled by inertial behavior. And so the idea here is that the flow comes in, it's happy to come along here until it reaches a stagnation point, it divides, and it absolutely hugs this surface as it goes out on this side, and it absolutely hugs this surface as it goes out on this side. So you can imagine that the fluid exerts on this some kind of shear force, which is due to this idea of viscosity being related to the gradient of the velocity close to this. So physically this means that the velocity on this contour is 0. As you go away from it, up here it would be equal to whatever the velocity is that's being supplied from the upstream. But here it has to be 0. So clearly if you plot, it's a bit blunt, my object is a bit too blunt. if you plotted a figure that was velocity with location, it would look something like this. The velocity here would be 0, and it would look like this, and therefore this gradient is quite high, and so the force that you'd expect to get from this would be large. The shear stress you get from this is large. Shear stress over an area is a force, and therefore the force is large. If you look at higher Reynolds numbers, then what you end up doing, it's not shown very well here. Actually, this is even higher, right? This is probably a better one. So this is 10 to the 5. So 100,000, not just 2,000, but 100,000. Then what you get is a boundary layer developed, which is a layer where there's lots of turbulence occurring, but it's quite efficient at moving things around. If you look at the velocity profile as you go from here, you'd find surprisingly that this external velocity u, which we have at this point here, as you come close to this, it would look much closer to being this, almost like a boxcar. That only when you get very close to this surface does it go to being. So you have a very large gradient here, which would suggest a very large shear force, but that's kind of isolated because you have this flow occurring on that boundary layer, which is actually quite efficient. And so there are two things that are important here. One is that now the drag on this is made up all of this changing in velocity that's occurring here. And this velocity term here, you remember, is this. So this, by definition, is velocity. So this is mass times rate of change. Well, actually, you can do it just like this, right? So you can do it just like mass times acceleration is just the same as mass times the rate of change of velocity, which is exactly the same as the rate of change if we just take this inside here. So this is rate of change of momentum. So rate of change of momentum is exactly what this term is here is. And by making all these eddies and currents, you can think of it as basically being the stagnation occurs here. It's so fast, the velocity goes to some very small number, and therefore this is the same as pushing the truck off the apron at San Francisco International, that this is due to this destruction of momentum that occurs. And so there's these two very important regimes. And so that's the reason that we're interested in being able to do experiments in wind tunnels, because it's quite easy to get solutions for the laminar regime, but it's not so easy to get it from these different kind of geometries. So that's the first thing, is that these two different behaviors matter at these different regimes. The second is that we want the kinematic similitude, that the flow regime that you have around your model should look exactly the same as the flow regime you expect to have around your prototype plane when it's flying. And so if the flow regime around your model looks like this, and the flow regime around your A380 when it's flying looks like this, then you don't have similitude, and therefore you can't use the results. Because in the most basic form of what we're attempting to do is we want to have a graph of the forces on the structure versus the Reynolds number. We expect to have a relationship that links these, and so long as we're using the same Reynolds number in both model and prototype, we can use the same Euler number, and we can get an exact solution. So that's kind of where we're going with this. So that was maybe more of a diversion than we needed. I think I'm in the right zone here to find that piece. Okay. So kinematic similitude means that geometrically the flow regime looks exactly the same in the model and in the prototype. And if that's the case, then we presumably also satisfy dynamic similitude. So this just means that the Reynolds number of the model has to equal the Reynolds number of the prototype. And dynamic similitude means that the Euler number, typically, of the model is equal to the Euler number of the prototype. And so, if in your model, where the flow is at an appropriate Reynolds number relative to your prototype, you measure the forces that are applied. You have your airplane on the stick, or the Raptor gets picked up by lift, by the airflow around it. You measure that force, you measure the drag, then you can convert that into what the appropriate forces would be on a life-size structure. And so really this is just using, in its basest sense, it's using this idea that if you have these two main variables that control response, you have a relationship between them. Actually, you don't need to know what this relationship is, because if the Reynolds number of both the model and the prototype are the same, then you're always at this point. You're not anywhere along here, you're just at this one point. And if you're at this one point, then you can always define that this is this point here, and this is this point here. That's it. So that's the idea of similitude and how it might apply. And so the easiest way to show that might be just to do an example by hand. There's some in the book as well, which we can get to if we have time. But this is, just a simple idea of a model plane, contrived example, and a prototype. And so the idea is that we have a plane in a wind tunnel. Let's see how good I am at drawing this. This is the tail plane. Pretty good, don't you think? It has wing length. It has a wing width of the model. And we have a prototype which hopefully should kind of look the same. It has a wing length, or a span, I guess, of the prototype, wing width of the prototype. There's some velocity in the model, and I guess there's some force due to lift on the airfoil of the model. So I have some numbers for these. What are we going to do? So length of the model is equal to 1 meter. The width of the model wing is 1/10 of that. This is equal to 1 meter a second, just keeping life easy. And the force is equal to 1 Newton. So all of those are things that we could measure. We choose to do it with air. And so that means that there's a viscosity and a density of air. We choose to do this with air also. So they would have the same densities and viscosity, just to make it easy. And we use this length to be equal to, for the real plane is 10 meters. This is equal to 1 meter. And I guess the questions would be, in the prototype, what is the velocity we fly at? And at that velocity, what would be the force that we get out of it? So that's simple example. And so we just need to approach our 3 requirements. So geometric similitude, length of the model to the length of the prototype is equal to 1/10, right? The width of the model to the width of the wing of the prototype is equal to 1/10. So all of these characteristic dimensions are shrunk down. So we've satisfied that. So we've ticked off one of them. The second is kinematic similitude. So by definition, we want the flow patterns around each of these systems to look the same. And so that is that the Reynolds number of the model has to equal the Reynolds number of the prototype. That means that velocity, density, and some characteristic length dimension, it could be any of our length dimensions, and the viscosity of the fluid for the model has to equal the same for the prototype. We're flying in the same materials, and so we know that these will cancel out with each other. And so we have from that what do we want to know? We want to know what the velocity of the prototype would be. And so I suppose that would be the velocity of the model multiplied by the length of the model divided by the length of the prototype, which is this here, equals the velocity of the prototype. And so if you put those numbers in, the velocity of the model was 1 meter a second, the length of the model was 1 meter, and the length of the prototype was 10 meters. So that is equal to 1/10 of a meter a second. So that's saying that if we run this as equal to 1/10 of a meter a second, then we satisfy this requirement. And so that means that on this figure where we plot Euler number versus Reynolds number with this thing here, we're exactly at some, actually let me get rid of this, we're exactly at some point which is the same number of Reynolds number for each one, and therefore the Euler numbers should be equivalent to each other. We're at this point. So the third thing then is if we have satisfied this, then we can satisfy dynamic similitude. That the forces on the two structures are in harmony, if you like, are similar to each other. And so that is that the Euler number on the model is equal to the Euler number on the prototype, which means that pressure divided by rho v squared is equivalent for both of them. We know that force is equal to pressure times area. So pressure is equal to force over area, right? You can think of this as a pressure mismatch between what's on the underside of the wing versus on top of the wing. You know exactly that that's why planes fly. You have a lower pressure above the wing than you do below, so it gets pushed up. And so this net pressure multiplied over the area of the surface gives you a force. And the force is what you'd measure if you're in a wind tunnel. And so we can substitute this here. And so this would be that the force divided by rho v squared, and this an area is just, the area could be equal to the length times the width of the wing, or it could be L squared, or it could be W squared. It doesn't really matter. Let's use LW, and that is for the model. And this has to equal the same for the prototype. Running out of space a bit, but what we'd like to do, we'd like to figure out what this is. And so if that's the case, then we can rearrange it, I guess, in terms of this, that the force on the prototype is equal to the force on the model, and it's going to be the ratio of rho prototype over rho model, v squared prototype over v squared model, L prototype with prototype over L model. Am I missing anything else? No, that's it, right? And so if we do that, we have the force on the model was 1 Newton. Densities, we don't care because it's the same fluid. The length to the width ratio of the prototype, this is, each one of these is 10 to 1, right? So this is 10 meters and this is 1 meter. This is 1 meter and this is 0.1 meters. So this is 100 or 10 times 10 over 1. And Vp squared over Vm squared, well, what was it? The prototype was 1/10 of a meter a second. And the velocity on the other one was a meter a second. And so this says that this is equal to 1 over 10, so equal to 10 newtons. Oh, didn't square it. Squared and squared, right, because of this. So this is 1 over 10 times 10, and this is 10 times 10, so this is just 1 Newton. So the force on the prototype, it probably won't get you off the ground, but the force on the prototype, by just using this similitude, is that because where we exist, in terms of Reynolds number and Euler number, for both model and prototype, is some number here, then that's allowed us to calculate what the force is on the prototype, which is useful to us. But of course, we might be interested in not doing it at the same velocity, and so what then we'd need to do is we'd have to have some other corresponding experiments at different velocities to be able to say what's going on. But what we could do is we could hark back to this idea that we had from here. And that is that we know a little bit about what we might expect these force distributions to be as we change different Reynolds numbers. So for instance, although we've done it right now for a value which has given us the same number that has allowed us to go over here, if for instance where we were at our current Reynolds number was here, and we thought that the relationship would take us over here, then we can do something else. And what we could do is, if we thought that actually our graph looked like this, or that we were somewhere on here, then when we look at these different ideas of similitude, what we could do is now we could do an experiment that we know that if we do the experiment at a different Reynolds number, even if we don't satisfy this, that the drag or the lift is not going to vary as a function of Reynolds number. If we thought that our current experiment that we had here was at this location here, then we could choose to do it at a number over here. So what we could do is now we could violate this, and we could run our experiment at 10 meters a second, or 1 meter a second. So if now we choose in the prototype v equals 1 meter a second, then we could still use this expression that we have here, and we could calculate the force in the prototype if we run at this particular velocity, and it's going to be equal to 1 Newton multiplied by, where is our velocity? So this, instead of being 1 over 10 squared, is equal to 1 squared divided by 1 squared multiplied by, this is still going to be 10 times 10 over 1. So in this particular case, the force on the prototype would not be 1 Newton, but it would be 100 newtons it would pull out, which seems like something more realistic. And so these are the basic requirements of similitude that we can use. To use them strictly for a model, you have one point in this space if you have 2 pi variables, it's Euler number, If you do the experiment at exactly the same Reynolds number, then you have exactly the same Euler number. But we can use it more usefully because we know something about these behaviors, and that is that this behavior over here is this turbulent response, and this is this viscous response. And from what we understand about these two behaviors, we can actually be much more clever about the experiments that we do. Okay. Right? So I think it's a cool topic because it actually allows you to, you could use these principles in any experiment that you choose to do, not just in fluid mechanics, but in thermodynamics for that matter as well. What else? I'm not sure. You'll see lots of different, yeah, let's do another example just to cement the ideas. It often turns out that the variables we end up are Reynolds number, which defines the flow field, and Euler number that defines the forces that are applied on structures, but not always. So it depends on the system that you're dealing with. But you can always use this method to do it. And so this is just another example doing 7 things. Viscous fluid flows past a submerged rectangular plate. This drag force here, that hasn't come out very well. This is the drag force. Is a function of plate height and width. You can imagine that probably it's more a function of height than width, just because of the geometry. You know, you're smacking and you're stagnating against this big plate that has a width. I can't imagine that the shear stresses on the top and bottom, you couldn't imagine would make much difference. Models to be used to predict the drag using a certain test using glycerin with a certain viscosity and a certain size, and measures the drag force that's applied at a certain velocity. Is it possible to predict the drag on a similar plate that has different height and width and is immersed in the same liquid, so it has the same viscosity but with a different velocity? And so what are the variables that control the behavior? There's a force that's applied that holds this plate in place, which would be the reaction that you'd hold this with and measure. There's a height and width. There's a velocity of the flow as it comes in, and there's viscosity. And so this presumably is in this regime where viscosity around the system is hugging it. So the corollary of our cylinder in low Reynolds number flows would be this flow here, that it hugs this absolutely and comes off the back, so that all the forces that are applied on this are due to this flow. And actually, what I've just said now about this being a minimal component, this might actually be the large component, actually going around here, and the shear stresses that are applied on this face as this flows around due to viscosity, if it's at low Reynolds number, so Reynolds number is low, then you could imagine that we could throw this term away, throw this term away, because v squared over 2g, for which density has some impact from F equals ma, is no longer relevant. So we could go through this with Buckingham PI. We have 1, 2, 3, 4, 5 variables. If we have MLT all represented, then we have 5 minus 3 gives us 2 pi variables. And we could go through Buckingham PI to figure what they are. And because we don't have a density, we'd get neither a Reynolds number or a Euler number, right? Because Reynolds number is V rho H over viscosity, and Euler number is P over rho V squared. So where density doesn't exist in either of these, we don't quite get a Reynolds number or an Euler number. But you can check that this is a dimensionless number. These are certainly dimensionless, ratio of 2 lengths. And so we have to satisfy geometric similitude, which we do, because the model and the prototype are the same dimensions, apparently. And then we want to satisfy the other similitude, So I guess since we have 2 pi variables, then we would have B over h, and we'd have drag force divided by length, velocity, and viscosity. And we have, if we satisfy that this is true both for the prototype and for the model, then we basically have a point here. And so long as this is true, then this is true for both model and prototype, and we can use that to satisfy that, to calculate what the force is that's applied on the different shaped, different sized model relative to the other one, relative to a different velocity that's flowing as well. And so we just have to be careful to realize that in this particular case, we haven't used density here. If we had density, we'd have another term. My guess is if we use density, we'd also have a Reynolds number that we'd have to satisfy as well. And so we'd have to, if we satisfied this Reynolds number and this number and geometric similitude, then we'd have a solution. So that's what the this issue here is. Not possible. So we have to be careful in choosing our numbers. So this is clearly a case in which the Reynolds number is so low that we're within this part of the graph where Euler number, which is the same as the coefficient of drag, is in this region relative to Reynolds number. And so if we're in this region here, then actually it's not safe. We need to actually be at the same Reynolds number. So we could check in this particular case if we're the same Reynolds number, but actually we don't know. Yeah, I guess we don't need to know what the density is, right? We just need to know that it's the same fluid flowing past the model and the prototype. So we need to check whether the Reynolds number actually is consistent. So that's it. There are a couple of other examples. We won't go through those. We'll leave it here because we're right at time.